This is Dr. Daniel Dunay. I create evolutionary algorithms in C++ and Python. These evolutionary algorithms look at something you've measured, and they generate computer models. These computer models can be used to explain your data, or they can be used to predict outcomes given new data. Today we're going to be looking at polynomial induction. That is, finding polynomials in your random data. Let me grab a better microphone. I'll be right back with you.
Polynomial induction can be very demanding for an evolutionary algorithm. However, it can also be rewarding because it's easy to see when your computer models are simple and correct, and you know the precise complexity of the data you just figured out. I'm going to show you a technique to help your evolutionary algorithm discover the polynomials hidden in your data. First, let's look at some data. I've generated data from a polynomial. P1 equals x squared plus 2x plus y cubed. This is our training data. Given x and y's inputs, we are asking our program to discover the transformation that will produce polynomial P1. Now let's generate some more data by generating another polynomial from the output of the first polynomial. P2 equals P1 times x times y plus 1, which is to say x cubed y plus 2x squared y plus y cubed. You can see how quickly our problems get complicated by multiplying polynomials together. Our very simple training case becomes the following data set. Notice the outputs P2 and P1 are preceding the inputs x and y. Finally, let's generate some more training data by combining the first two polynomials. P3 equals P2 times P1 plus 1. In other words, the quantity x squared plus 2x plus y cubed times the quantity x cubed y plus 2x squared y plus y cubed plus 1. Now we see the three outputs and the two inputs. Although it's easy to generate this data, you can see how difficult it might be to reverse the process. What we really need is a way to combine the user's intuition about polynomials with the evolutionary algorithm's amazing search characteristics. Let's just refer to an evolutionary algorithm as an EA. Suppose we let the user make some guesses about what's going on. We don't want to take the user's guesses too literally, but we want to incorporate them. Suppose the user makes the following wild guesses based on polynomials they know. Now, let the user's guesses serve as templates for our random solutions. Let's look at the first guess. In the formula ax plus by plus cz, let x and y be random columns from the training data. Let's let a, b, and c be random coefficients. Let's not ask the user for the coefficients. The EA is great at finding optimal coefficients. Likewise, let's not ask the user to map the variables to the columns of data. The EA is great at trying the possibilities. Remember our complicated training data? Let's see what the EA does when we incorporate the user's guesses. First, we see our data with 2 inputs and 3 outputs. Next, we see the formulas which guide the creation of a portion of our random solutions. This is a solution to the easiest problem, polynomial 1. This is the next easiest problem, polynomial 2. It used polynomial 1 to solve the more difficult problem. The last solution uses both of the previous solutions. Finally, we see all three problems depicted as binary trees. The first tree reads as 2x plus y cubed plus x squared. Rearranging the terms, we see the polynomial that generated this data, x squared plus 2x plus y cubed. In the second solution, we're looking for polynomial 1 times x times y plus 1. The binary tree reads as 1 plus y times x times polynomial 1. Rearranging terms, we see the polynomial that generated our data. The third solution reads as polynomial 2 times polynomial 1 plus 1. Exactly our input equation. Testing shows that adding input formulas decreases the solution time and often makes a difference between finding the solution and not. Interestingly, adding the formulas decreases the time required for a solution, even when formulas similar to our problem are excluded. The EA quickly rearranges the input formulas that remain to produce the correct output. I hope you've enjoyed this quick look at polynomial induction.